Thank you for having me speak. It's been a real pleasure to hear other speakers this afternoon as well. Talking to you here about structural engineers' role in the design process and the process of reducing the consumption of material consumption in our buildings. Title here being optimization, but ultimately I want to show and give you tools to challenge your structural engineers to help you in the process of material efficiency, but also in those strategic beyond just optimization and before you get to an optimization process, in challenging strategic elements of design brief and approach to design. Right. Oh, my slides advanced. There we go. So just to remind us, we are there is a climate emergency. It is an emergency, and it requires action now for immediate reduction of atmospheric carbon. So this was a slight revelation to me a year or two ago, in that we need to be thinking about doing everything we can do at this moment in time to reduce the emission of carbon emissions, not planning for future options and adaptabilities, and very much ties back to my education as a structural engineer, mantras that were embedded on me on touching the earth lightly, so using as little material as possible. I was asked just to touch on what this means and what embodied carbon is, because embodied carbon is this process or the challenge of all of the materials that go into the building, the physical building fabric. And this is the process of creating the materials that go into our building, and the process of bringing those materials to site. Carbon dioxide is not the only greenhouse gas that contributes to the greenhouse effect. There are others, and actually, it's not just about carbon emissions. It is also about other environmental degradation and pollution, and use and consumption of other natural resources. And the next big challenge to us, or the current big challenge to us alongside carbon emissions, is also around water consumption globally. So just thinking about where this fits into the life cycle of a building, and what I'm going to be talking around is the use of materials. Currently, a large amount of our focus when we're talking about around materials is this cradle to gate. It's the area in which current data is set up and provided, be that through carbon inventories, product environmental declarations and such like. But this is one component of the whole life cycle of the building, and it's great to hear about the presentations on circular economy and beyond, and therefore just really reiterating the fact that the right decisions have to be made first of all to make sure that our natural resources being invested in buildings are made before we commit to using and consuming more materials in the specification and construction of a new building. We need to know where we're aiming for, and I'm sure you in this conference have already discussed the RIBA climate challenge. This has been actually, as a structural engineer, very useful for us. As a profession, you're one step ahead of the structural engineers. We do not have we do not have road mapped out for us the challenge and the reductions which we need to make. But actually, we've taken and our practice have taken this and looked at how and what we need to do to be able to drive this embodied carbon reduction. But very importantly, this is hand in hand, obviously, with the operational energy of buildings. Our practice and within the structural teams within Buro Happold, it's always good to know the context and the influence that we have. the purple, blue, and grey pie chart on the left is taken from from RICAS data, and then looking at actually where the engineer is responsible, but also actually it's not just the engineer that is responsible, and you'll see this in the study that I'm about to present. It's not just the engineer that is able to influence the amount of carbon that goes into the superstructure and substructure, and then also the embodied carbon that is manifests itself within the fit out of a building also can be influenced by the structural engineer and the design team as a whole. So where do we start from? It is important to understand where in the structure the carbon, the embodied carbon is, and this is our accumulation of literally hundreds of building assessments, embodied carbon building assessments, and trying to rationalize that that data and just bring it down to give ourselves a picture, so it helps us understand our approach and where the target for potential reduction in the building structure, and clearly here common theme, no matter what methodology has been used, the floors of a building contains by far the largest proportion of the embodied carbon. So seeing this, something which frustrated me was the design team, the design conversations we had alongside our building services colleagues around that weren't data driven, that were based around hearsay, around and I felt that as structural engineers, our colleagues who designing building systems had a far better handle on the carbon emissions from a building. So we commissioned quite a lengthy study that helped us understand what measures we could take to drive down carbon within a building. So we took a hypothetical building frame. Here it is in front of you here. It's 9 meter by 9 meter, 6 stories, and we designed this fully for an imposed load in a standard concrete flat slab solution, a steel frame with composite deck, and a glue lam and cross-laminated timber slab. And fundamentally now we need to be very familiar with numbers and the quantities of embodied carbon. This is our new currency, if you like, for building design. And those numbers within the circles, you'll see these come up time and time again throughout this study. These are kilograms of carbon dioxide per meter squared of these frames. So here is our baseline set of figures for these structural frames. So then we went about varying individually, item by item, different parameters within the design to see what impact that had on that per meter squared embodied carbon rate for the building. Looking at, and in this case, you see horizontally across the line is our baseline, 331 kilograms of carbon dioxide per meter squared, and then starting to vary different parameters, looking at cement replacement, looking at reducing the column grid from that 9 meters down to 6.5 meters. Challenging ourselves around concrete grade. What happens if you have a higher concrete grade and less reinforcement, higher quantity of reinforcement? Does that mean that we can reduce our slab thickness? Looking at the loading on the building frame, same geometry, but what happens when we just start to pare back that imposed loading that we design our building and optimize our building for? And we did this all the way through all of these different parameters, and each figure there is what that manifested for that one variation within the design of our structural frame. So we did exactly the same thing for looking at the steel frame. We took our baseline scheme. We then started to reduce and increase column grids, looking at depths of the decking, looking at the foundation solution, and for each variation we recalculated all of the parameters within the structural frame. And then also looked, in the case here of steel, what happens when we replace the concrete composite slab with cross-laminated timber deck. And once again, we took an approach very much of, just because it's a timber structure doesn't mean to say that this is as good as we can make it. Again, looking at how we can optimize the structure, the different systems, and the different approaches to that. Looking at foundation thickness, looking at imposed loads and column grids, looking at different solutions of different types of timber products, and seeing how these can improve or reduce the embodied carbon of the overall structural frame. So we would never actually do this as a one by one in a design for real. So looking at this sort of slug trail around this was looking at all of the different components that we could integrate together to try and see how low we could go on our embodied carbon content of our structural frame. I'm doing this not only for the concrete solution, but for the steel solution and for the timber solution. And importantly here, really looking to see that there is significant potential to drive down the embodied carbon. But what you've seen here in some of those parameters that I've shown you is that these aren't decisions that the structural engineer alone can make. Persuading clients to accept a reduced load, or reducing the column grid is a collective team decision, and client decision, and operational decision, but something which has a significant impact. And there are a significant number of different conclusions that came from this, but really to try and keep this high level and key. If I was to say, what are the top things that you can challenge your structural engineer to help you with, I would say loading. Loading is a significant challenge. We over-specify, in our opinion, the loadings of buildings, sometimes with good intent for future adaptability and flexibility. But again, back to that opening slide, we are at a climate emergency. We have to act now, and we have to reduce and eliminate carbon emissions, atmospheric carbon emissions. It's very important just to think of that in the context of the overall design. This is quite an old study that was done by University of Cambridge and Bath, but absolutely setting the challenge out for the structural engineering profession. We design buildings for ventilation, space planning, and fire regulations that are well exceeded by our loading capacities of the buildings which are occupied, and the structural load capacity never in the lifetime of the buildings is anywhere near realised. Column grids are, I mentioned earlier, and was one of the key parameters for change. If you think about this in seeing that early slide of where the embodied carbon is within a structural frame, it's in the floor, and if we can reduce spans on floors, there's significant savings to be made of embodied carbon within floor structures. But I guess just rapidly sort of concluding on this, that with this new currency of measuring carbon within buildings, knowing where the carbon is, and then looking at this on a case-by-case building study is really important. Being able to specify a building to get the best and lowest carbon outcomes is a key step, but then allowing time for optimization, for integration, and for detailing that allows you to drive down the embodied carbon, and the design engineers to be able to drive down the embodied carbon is super critical. In line with our commitments and climate emergency declarations, all of these studies are open source, there to be challenged, there to be developed and built on. This is published through the Institution of Structural Engineers, and it's available there. It's also available through the Buro Happold website, and I would welcome you to download and ask any questions.
Thank you very much, Andrew. Could I just ask a couple of questions, if I think we've got time for a couple of questions?
Absolutely.
Inevitably, there's a bit of a debate starting on the chat around balancing embodied carbon, so getting the benefits of embodied carbon savings now versus that kind of over-speccing or maybe larger spans that you might need for future flexibility. How do you think we sort of find that sweet spot that enables us to kind of, get that circular economy thinking to, include those short-term savings in embodied carbon, as well as not sort of, I guess, stacking up problems for the future?
I guess there's a few things around that. If we're serious about atmospheric carbon emissions, we have to start around absolutely driving out and challenging the issue now, and therefore using as little material and creating as lower emissions now. If on that, and part of this I probably didn't explain too well, but this issue around our building services colleagues being very good at measuring, maybe not always as good at achieving, but very good at measuring the operational carbon emissions of buildings. But we need to be able to look at that now in the whole life of the building, and actually be able to measure and look at how you drive down the embodied carbon as part of that. So, the number of times I've looked at needing thermal mass in buildings, people being told that we need thermal mass in buildings, but actually these are sealed boxes that don't have openable windows, and therefore the benefits of purge cooling and things like that aren't there, which undermines that type of argument. On the question of sort of future flexibility, we don't know which way technology is going. The COVID crisis has taught us that we can absolutely change the way that we behave. So space standards, column grid spats, etc., are built around a set of expectations and the way that we historically have used buildings, but we need to, if we're serious, we need to adapt our behaviours and accept compromise and challenge the way we behave. So I think that there's an urgency about things, and that urgency is accepting that in the future we may have to overcome different challenges of adaptation of buildings when we start to use them, but that isn't here with us now, and we do need to start driving or continue to really push down the embodied carbon contents of our buildings.
One very quick fire question, which is really about this comment around kind of massive overspecking of structural systems, which probably goes back many decades. So we've probably got huge amount of redundancy in building structures. Don't know if there's anything we can do about that. But, what needs to change, in terms of regulation, in terms of, as you said, kind of attitudes and behaviours of clients and engineers to ensure that we really are optimising structures moving forward?
It's interesting. Quite a few of these things are built around, for structural engineers, around codes and standards. And actually then it's a challenge around insurances of buildings. I don't want to open a can of worms here, but being a very pertinent current topic, but quite often, particularly in the past when I've worked on projects where we've reused foundations on buildings and such. Like anything which deviates away from code requires a significant amount of effort from the design team to actually not overcome the technical challenges, but usually the commercial challenges that are around, be that reuse of building components or deviation from design codes and standards. So I think that there is a challenge to the structural engineering profession as well, to look at the codes and standards, but that we use. One element I failed to touch on within that rapid run through was serviceability of buildings and over specifying deflections for facade systems and such, like looking at where and brittle finishes within buildings. Can we specify greater levels of deflection and use systems that don't require very stiff structures, and very much within that realm there is massive opportunity to reduce carbon in building frames.